Welcome to Variational Principles and Lagrange's equations. Today we are going to discuss the advantages of a variational principle formulation. Hamilton's principle in the form of equation 2.2 is most useful when a Lagrangian of independent coordinates can be set up for the system. It contains all of the mechanics of holonomic systems subjected to forces derivable from generalized potentials. It involves only the kinetic and potential energies and as such is invariant to the choice of coordinates. Recall that in the previous chapter we have shown that Lagrangians produce the same equations of motion up to a, a a total time derivative of a function of a general function given in terms of generalized coordinates and time, which we call the gauge function. So Lagrangians being constructed through the use of different forms of such gauge functions produce the same equations of motion. And we can understand that on the basis of Hamilton's principle very easily, because if we write the action integral down and the action principle for a given Lagrangian, then by adding such total time derivative to it, the contribution of this term is just the difference in the values of the function at the endpoints of the path integral. But since the variations at the endpoints are null, it is clear why the variational character of the integral is unaffected by such a gauge function, and why the Lagrangian is uncertain up to its total derivative with respect to time. Another advantage of the variational formulation is given by the treatment of dynamical fields, be they the elastic or electromagnetic fields, or the field properties of elementary particles. In the following, we will discuss some simple applications of the formulation to classical electrodynamics. The first such application is the simple case of a source of voltage V in series with a resistor R. In this case, the potential energy provided by the voltage source is just minus the charge times the voltage, and as such, the Lagrangian of this particular circuit is simply the charge times the voltage. And to it, we must add a dissipation function describing the resistor, which is simply 1 over 2 times R, which is the resistance times the square of the current flowing through the resistor. As such, the Lagrange equation can be constructed quite easily. The term involving the generalized velocities is obviously vanishing. The term involving the generalized coordinate, which is the charge, is just the voltage, and the dissipation term is the product between the resistance and the time derivative of the charge. So the equation of motion is simply V being equal with R times the time derivative of Q, but the time derivative of Q is obviously just the current flowing through the resistor. So the end result is simply the well-known Ohm's law for a steady-state current, which says that the voltage across a resistor is given by the product between the resistance and the intensity of the current flowing through the resistor. A slightly more general example involves a source of voltage V in series with a resistor R and an inductance L. So what happens in this case is that the inductance plays the role of a kinetic term. So the energy contribution to the system, as the expression here, where you see it looks like the dissipation function, but it does not have the physical significance of a form of dissipation. Rather, the inductance plays the role of mass, and the current plays the role of the velocity. So this whole term is a way of expressing the kinetic energy of the circuit, and the potential energy is once again given just by the product between the charge present in the circuit and the voltage provided by the source, such that the Lagrangian has the structure here, to which we also added dissipation contribution from the resistance. And then if we work out quite easily the partial derivatives that are involved, we find the equation of motion here, which should already look fairly familiar from and fairly similar to an example that we've studied in chapter 1. In that case, it was involving a particle just falling through the planet's atmosphere under the influence of gravity. And we can see the analogy by identifying once again the time derivative of the charge of the electrical current, case in which the equation takes the form here. And we know how to solve this from that example. We look for a current being given by a function of time plus the constant, which is just the ratio of voltage to resistance. And we have the initial condition that at t equals 0, the current flowing through the circuit was null. And then just by a straightforward solution, which is identical to the way we solved that problem, we find the current as a function of time, having the expression here with I0 being the steady state current given by V over R. So it is, once again, this is just Ohm's law for the steady state regime of this circuit. So you see that the contribution of the kinetic term is essentially that of giving the system inertia and a dynamical resistance to in going from the initial state of, let's say, rest to the steady state given by Ohm's law. And as said previously, the mechanical analog is a sphere of radius a and effective mass m prime, falling in a viscous fluid of constant density and viscosity eta under gravity. The effective mass is the difference between the actual mass of the sphere and the displaced mass of the fluid. And you can see the complete structural analogy between the energy terms describing the mechanical example when compared with the energy terms describing the electromagnetic case. So the kinetic energy is the same thing. The potential energy is the same thing. I'm using slightly different notations, but it's quite clear that so here y plays the role of the y coordinate of the particle of falling through the fluid plays the role of the electrical charge, and the product between m prime and g plays the role of previously played by the voltage. And the dissipation function once again has the same structure in terms of the square of the generalized velocity times constant. And of course the equation of motion is structurally identical. I've written the terms in a slightly different order, so this potential term corresponds to the voltage here, and the dissipation term here corresponds with the one here. But obviously, if we use if we seek a solution of the same form and use the initial condition of the particle being at rest at t equals 0, then we obtain a formally analogous solution in terms of a steady state velocity v0 and the logarithmic decrement, if you want, tau, given by the ratio here. And just as a basic illustration of the two cases, I've plotted here as a function of time in seconds an electrical current in milliamperes and a velocity in millimeters per second with so the current is given by the formula here and the velocity by the result here. The current is drawn with a continuous line while the continuous curve, while v is given by the curve with dots and dashes, and you can see that formally they behave in exactly the same way in going from 0 to their steady state values. So these two dynamical systems, though they are they correspond to what appear to be very different physical situations are in fact formally and structurally completely analogous. A third example is the one of a circuit consisting of an inductance linked with a capacitor of the potential energy Q squared divided by 2 times C, where C is the capacitance. And it is clear then that the Lagrangian is going to be the kinetic term, the difference between kinetic term and this potential term, which leads to what should be a very familiar equation of motion, and particularly for the following initial conditions. So for the charge Q at t equals 0 being some value Q0, so this is the charge on the capacitor, and the initial current through the system being 0, then the solution is simply Q0 times cosine of omega t, where omega squared is the ratio of 1 to the product between inductance and capacitance. So the mechanical analog is the simple harmonic oscillator of frequency omega being equal with the square root of the spring constant divided to the mass. And in summary, our conclusions would be that the inductance is an inertial term, so it's the electrical analog of mass. The resistance is a dissipation term, analog of Stokes type of frictional drag. And the capacitance is written as 1 divided by C is the analog of Hooke's law elastic spring constant. Now, for general electrical systems made out of coupled circuits, Lagrangians can obviously be written as a kinetic term involving all of the inductances, a potential term, or a capacitive term given by the potential energy of all of the involved capacitors, a potential term being given by the voltage sources or the electromotive sources present in the system. And if the circuits are coupled, we also have terms of mutual inductance, which this can be understood intuitively, and the idea of current carrying wires that are interacting with each other. But to understand exactly where this term comes from, we need to do a more thorough study of classical electrodynamics, and hopefully we will go through that at some point in the future. In any case, to this Lagrangian, we need to add a dissipation function, which includes the effects of the dissipative effects of all of the resistors present in the circuits, and as such the equations of motion follow immediately through the prescription presented here. Having gone through all these things, we can now discuss the slightly more complex case of a Wheatstone bridge. So this type of circuit consists of a voltage source leading to two branches of the circuit, which are connected through a bridge featuring a current measuring device. And such a system will feature the voltage source, the current measuring device or ampermeter, the four resistances, and four junctions, which I've labeled as A, B, C, D, or one, let's say 1, 2, 3, and 4, respectively. And this is an example of a dynamical system where the method of Lagrange's undetermined multipliers is useful in and solving the system and finding the network equation, which are given by the empirically given by Kirchhoff's laws. And so for the four junctions in the system, we can write four constraints or currents, which are just a way of expressing charge conservation. So essentially the current that goes in must be equal to the current that goes out. And then in that case, in each junction, we have the following set of equalities. So for example, for the first junction, the ingoing current I has to be equal with the sum of the outgoing currents. So it's minus Q1 dot minus Q3 dot, and so on. So for each case, the ingoing current I3, for example, will be, in this case, I3 and I5 coming from the bridge must be equal with the outgoing current I4, and so on. So these are the constraints. And then obviously the potential energy is given by the product between charge and voltage across the four resistors together with the voltage across the bridge, assuming the system is imbalanced. And the dissipation function is, of course, given by the 5 terms corresponding to the dissipation across the four resistors and across the bridge. So then the Lagrangian is given by this potential term, to which we must add the four equations of constraint, each multiplied with its own undetermined Lagrange multiplier. And this leads to a set of 5 equations of motion. But if we then proceed to eliminate the multipliers among these equations, we actually end up with just a set of two independent equations, and these are nothing more than an expression of Kirchhoff's second law for the two loops in the circuit. So for the loop here and the loop here. And now if we consider that the bridge is balanced, so for example, let's say that this resistance is unknown, R4, but we know R1 and R3, and then we can adjust R2 such that the voltage across the bridge vanishes. Then in that case, the equations reduce to the result here, and of course, since these two must be equal, then of course the current going through the two the current on a given branch between the two sides of the bridge must be the same, since there's no current through the bridge, and as such, so we will have these currents are equal and these currents are equal, and then what follows is that we find R4 simply as the product of, should be the product of these two divided by the product of R1. So this is a way of solving a Wheatstone bridge using Lagrangian dynamics and Lagrange's undetermined multipliers. And in a straightforward, slightly more general extension given by the so-called modified Wheatstone bridge, we can simply add an inductance cell on one side of the bridge and on one arm, and a capacitance in the other, and of course then the Lagrangian will have two additional terms, the kinetic term here and the capacitance term here, but it leads to very similar equations involving the kinetic term and the capacitance term. We have seen that equivalent electromagnetic problems can be formulated for mechanical or acoustical systems and vice versa. Terms like reactance or susceptance, once specific to electromagnetic systems, are now found in descriptions of vibrational or mechanical problems. Variational principles can be used to derive equations of motion. be they Newton's equations, Maxwell's equations, or the Schrödinger equation. So as a comment here, we have seen that Newton's equations follow from Hamilton's principle. Likewise, Maxwell's equations follow from a classical action principle, but Schrödinger's equation can be derived from a quantum mechanical version of Hamilton's principle. So in any case, when this is possible, so when theories are derived from general variational principles, then to a degree all of these different fields of theoretical physics exhibit a form of structural analogy. As such, when experiments show the need to alter the theory describing a specific field, this analogy suggests how other fields should change. A particular example is the quantization of the electromagnetic radiation. The method itself was originally developed for elementary particle physics, starting from the Lagrangian formulation of classical mechanics. By describing the electromagnetic field through a Lagrangian and the corresponding Hamilton's principle, one carries over the methods of particle quantization and constructs a quantum electrodynamics. This whole statement might be a bit ambiguous or confusing as to what exactly the authors meant to say, because historically I believe that so the quantum mechanical formulation in terms of Schrödinger's equation describes quantum systems, like for example the bound states of atoms, but in terms of classical fields. So for example the Schrödinger equation for the bound states of a hydrogen atom produces a quantized spectrum, but assuming that the electromagnetic field within the atom is described in terms of a classical potential. And the first proper quantum field theory was in fact the theory of quantum electrodynamics in the formulation of Paul Dirac, even if it wasn't a complete or a final theory of quantum electrodynamics, as it went through a long series of developments over the decades, which eventually culminated in the standard model of particle physics and of elementary particles and fundamental interactions. And this is, if you want, the relativistic branch of development. But as the relativistic theory of quantum fields was developed, a parallel branch followed in the non-relativistic regime, and it also originated with Paul Dirac's original description of quantum electrodynamics, as followed from the works of Vladimir Fock or Douglas Hartree. And this non-relativistic theory is the basis of the many-body theory, which describes quantum systems made out of many particles that are strongly interacting with each other. So the multi-electron atom, or the atomic nucleus, the physics of condensed matter systems, and so on. So as a summary, in this section we have explored the advantages of variational formulation of classical mechanics by applying the Lagrange equations to various electrical circuits and discussing their similarities with specific mechanical problems. In the following, we will discuss conservation theorems and symmetry properties of dynamical systems. So I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.